everyone at Ashoka for inviting me and hosting me. Is that something wrong with that? Okay, yeah. It's very nice to be here. Very nice campus. My first time here. I hope I'll be back again sometime. So as Sandeep has asked me, so my talk will not be very technical. As I understand, the audience is also quite varied. So I'm going to tell you about some problems largely in probability theory, but they have connections to various combinatorics, statistical physics, various other branches of mathematics. So I'll problems and a little bit about what is known. So since it's meant to be not a very technical talk, I'll not really be talking much about what I have been doing. Maybe at the end, if we have time, I'll spend a couple of slides on that. But so what is that we are trying to do here? Can we remove this panel? No, this okay, thanks. Okay, yeah. So what is that we are trying to understand here? So there are many real world situations where you see some growing clusters or some phenomenon of growth which is not really deterministic. So if you're coming from more of a computer science or networks background, you might want to think of an examples as like spreading of rumor in a network or spreading of information in a network or spread of infection. So you start with some infected vertices and there's some stochastic rule which tells you how infection spreads along the edges of the network, and you want to understand at some large time which are the nodes that are infected. More from the statistical physics of side of things, you might want to understand that there is some porous media. So I have some medium through which water can pass, but how fast the water can pass through it depends on the strength of or the porosity of the medium, and you model that by some sort of randomness in the medium, and you want to understand how long does it take for water to percolate through one side of a block of soil to the other side. So there are many such examples, and I mean this picture is a picture of snowflake aggregation. So how snowflake aggregates on ground when there's snowing or something like that. So there are many models, or you can think about how forest fire spreads. So there are many such instances where it might be useful to understand how these sort of growth, where there is no clear deterministic pattern that are affected by various stochastic parameters, how they behave in large scale. So that is the broad question that we want to understand. So of course, if you want to do mathematics, this question is very ill defined. So what we aim to do is that we aim to define some simple enough models which can be analyzed and hopefully can mimic some of the behaviors that you see in these real world growth models. That's sort of the broad goal of this area. But before that, let me show you some pretty pictures. So this is a picture of a cancer cell. So this is in some cancerous tissue, the boundary of, so you start with the cancerous part of the tissue is somewhat small, and then it grows with time. So this is the boundary of a cancerous region in a cancerous tissue. These are real world pictures. So this one is the boundary of a growing bacterial colony. So you have a bacterial colony that starts from some point or some initial state, and with time it grows by aggregating the neighboring region into its colony. So this is a bacterial colony. No, sorry, actually I'm wrong. So this is not the one that will come in the next slide. So this is actually the front of a burning paper. So you burn the edge of a paper slowly, and I mean, if you have done that like I have done in my childhood, you will see that there is this jagged line formed at the boundary, at the front of the burning front of the paper. So this is these jagged edge is basically the front of the burning paper. So that's these are all again like real world experiments. So this one is the bacterial colony. So this is the colony of E. coli bacteria that is growing with time, and this is sort of the edge of the colony at some large time. And this one is what is called a ballistic deposition. So this is not actually real world experiment, but this is something like you have these dominoes falling randomly at a substrate, and whenever you stick to the existing cluster somewhere, you kind of stick there. You don't go all the way down. So if you have played a game of Tetris ever, so this is like a sticky version of that. That's why it's called sticky Tetris. So all of these models kind of give rise to these rough interface at the top. So you're looking at the top envelope at some large time after you have run this process, and you have this jagged, somewhat rough interface that is forming. And we want to understand that how are these interfaces forming? What are the large-scale characteristics of it? And can we somehow describe these large-scale behavior via some simple interaction? Okay, so that is what the goal of this this subject is, at least at the beginning. So let's try and come up with a model, a very simple model that will try to mimic some of these growth models. So this is a model that was introduced by Murray Eden, who I think was an electrical engineer by profession in 1961, where he introduced this as a model for growing bacterial colonies. But let's see how the interface grows. So this blue vertex at the center, at time 0, it's the only infected vertex, or it's the only vertex that is occupied by the bacterial colony. And then at each subsequent time, what you do is that you choose a random neighbor of the currently occupied cluster. So I have these 4 vertices marked in red, which are 4 neighbors of the currently occupied cluster. And then you expand the cluster by adding one of these 4 chosen randomly. So maybe I choose this one. So now my cluster contains these 2 vertices, and I have 6 neighbors. At the next time step, I choose one uniformly out of these 6, and I have this cluster of 3 vertices and this updated set of neighbors, and I move forward in time like this. So this is called the Eden model, which is a very simplified model for bacterial colony growth or any other kind of random growth. You can do this in other background geometry also. It doesn't have to be 2-dimensional lattice. You can do d-dimensional lattice. If you want, you can take any other graph. You can take Cayley graph of finitely generated group. You can take random graphs, whatever your favorite background geometric object, whatever you want, you take it and you do this process. So that will define a random growth process in some background geometry. And you want to understand, so 2 questions. So first of all, can you analyze this process? So if I ask you what happens if I let this process run up to time 1 million, what will the set of blue vertices look like? That is one question. So that's a mathematical question. And one other question, which is maybe of interest to practitioners or who are actually interested in how good the model is that does this model explain the characteristic that you see in these real world situations? Okay. So let's first talk about the first question and phrase it in a more general version. So this is the model of first passage percolation that was defined in 1965 by Hammersley and Welch. I mean, they were trying to model this fluid flow example of fluid flow through porous medium. But you will see that this model is essentially the same model as Eden as before, only slightly general. So what is this? So I have again a lattice, and at the edge of the lattice, I assign IID independent and identically distributed non-negative random weights. Okay, so this XE, so to each edge E, I assign this XE. So this edge is 1, this edge is 4, this edge is 1, and so on. And if you are a mathematician, you can just think about this as a perturbation of the L1 metric on the graph, on the nearest neighbor graph of Z2. So what I'm doing is that I'm taking any path. So the length of the path I calculate as just sum of the weights. So this path 1 plus 4 plus 1 plus 2 plus 4 plus 1 plus 3 is 16. And I can define a metric just by looking at the minimum length of a path joining 2 points. So this defines a random metric on Z2, which is called the first passage percolation metric. And how is this related to the previous model? So if these random variables are distributed exponentially, that means, because of the memoryless property of the exponential distribution, for those of you familiar with that, it means that whenever you reach a new edge, so start from 0 and look at the metric ball growing with time. So whenever you are reaching a new vertex, so you ask, so at time 1, I have a metric ball, certain random clusters of vertices. I ask what is the next vertex that is going to be included into the metric ball as I increase the radius of the ball. Because of the memoryless property of the exponential distribution, the next vertex included will actually be uniformly chosen among the neighbors of the currently included vertices. So this is a variant of a special case of Eden model where the edge weight distribution is exponential. So, I mean, here once I make the realization of the edge weights, then everything is deterministic. But if I do not expose the edge weights, so I am just exploring from origin, what is the first vertex to include it. So say this is the origin. At time 1, this vertex becomes included. At time 2, this and this becomes included. So I keep increasing time and I explore in a Markovian way. It will be Markovian because of the exponential, memoryless property of the exponential distribution. So I can ask, given that at time t, these are my vertices in the metric ball, what is the probability that this vertex is going to be the next one included in the ball? No, they are determining the metric ball at the current time. So I'm looking at, say, at some fixed time t, I look at all the set of vertices v such that t is 0 comma v, which is the distance in this random metric from 0 to v, that is less than equal to t. So that's some set. Maybe I should have a picture somewhere here. Yeah. So look at this picture. So at some time t, these are the vertices that are included in the cluster at time t, which means that which have the random metric from the origin less than equal to t. And now given this cluster, you can ask what is the next vertex outside this region that will be included in the cluster as I increase t. And if the distribution is exponential, then memoryless property of exponential tells you that all of the vertices which are neighbors of this current cluster, they will have uniform, all of them will have equal chance to be the next vertex included in the cluster, which is exactly the same as the model that Eden defined. So this you can think of as a generalization of the model that Eden defined. So this is called the first passage percolation. Yes. So exponential comes from the fact that if the distribution is something else, then my clock is running, right? So at time 1, this has been included, but this clock already has run 1. So what I need to do is I need to look at the residual life of that clock. So the property of exponential guarantees that the residual life has the same distribution as the full life. So this is the memoryless property of the exponential distribution. So if you have an exponential distribution, if you condition on it to be bigger than t, then the conditional distribution is t plus another exponential. So this is the memoryless property of the exponential distribution, which will make this growth a Markovian growth if you start with exponential distribution. Okay. So this is basically what I had already explained, that this metric, you can think of it as the wetting time. as in you start with some water at vertex u, and TUV, which is the metric that is in this fluid flow model, where the edge weight is the time you need to wait for the water to spread across that edge. So this TUV, this metric, is also has the interpretation that if you start with some fluid at the vertex u, TUV is the first time the vertex v becomes wet. So all of these things, I mean, all different interpretations of the same model. Okay, so as I already said, so this you can define in any arbitrary graph. It's actually quite interesting to do this on more general groups, like some non-abelian finitely generated group, and you can do it in Kelly graphs of that. But again, today I'm not going to talk about that. So this is, if you are a mathematician, maybe the most natural way for you to think about it is that it's a random metric. So you're distorting the metric structure of the background graph, which was the L1 metric. You're distorting it by putting these random lengths on the edges. So all these things I have already described. So what do we want to understand? What are the things that we want to understand? So we want to understand how this random length behaves asymptotically, as the distance, the deterministic distance between 2 points in the graph, as they become large, how does the random metric behave? How the TUV, this first passage time metric, how does that behave as u minus v becomes large? A very related question is the asymptotic ball of this asymptotic of this metric ball. So you can see this looks like it's some regular-ish shape, right? I mean, some fluctuation around a curve, right? So that's kind of what we want to understand. So is there a deterministic shape around which it fluctuates at a smaller scale? And it turns out that to understand these questions, it's also very important to understand the behavior of geodesics in the metric space. So I have a random metric space now, which it's not very hard to see that if you assume some very mild conditions on the random lengths that you imposed, this will be a geodesic metric space. So there will be geodesics, and you want to understand how the geodesics behave. Do the geodesics in some large scale sense approximate the Euclidean geodesic? Or if they don't, how far can they fluctuate from the Euclidean geodesic? And it may be not obvious at first, but it turns out that to understand that these two questions, you have to understand the questions about behaviors of the geodesics. Okay, so let's start with something very basic that everyone who have taken like an analysis course would find it very easy. So I want to understand, say, the expectation of the metric between 0 and n in some distance. Now observe, just by triangle inequality, it's a metric. So to go from 0 to m plus n, you can do at least as good as to go from 0 to m and m to m plus n. So that's just the triangle inequality. Take an expectation. Now, because the underlying environment is translation invariant, when you take an average of the distance from m to m plus n, that is the same as the distance, average distance from 0 to n. So you get this inequality which says that expectation of the distance in expectation of the metric in distance m plus n is less than equal to the expectation in distance n plus expectation in distance m. So it is a subadditive sequence. Now you must have seen Peckett's lemma, which will tell you that the first order growth is linear, and if you look at the expected value of xn and you converge and you divide by n, it converges to some constant. And it takes some work, but not very hard to show that if you put some nice enough, I mean very mild assumptions on the distribution, this constant can neither be 0 nor be infinity. So it will be actually a finite constant. Some mild assumptions which I won't get into that. You mean, is there a formula?
Is there a closed form?
No, there is not a closed form, because it will depend on the distribution f, right? I perturbed it randomly, so it will be a function of the distribution, and there is no closed form even for some some specific case of distribution like Bernoulli or uniform, there are no closed forms. There are closed forms in certain related models, which I'll describe maybe in a couple of slides. But in general, that's been a major problem, that you don't really understand this except some generic properties. There isn't any closed form yet. So x sub 0 comma m, yes. So x sub 0 comma m is what I am abbreviating. So if the first coordinate is 0, I just abbreviate it by x m plus n. So x sub m, that is just x 0 comma m. So 0 comma m is that 0 0 to m 0. So I'm going in the first x-axis direction, distance m. But you can look at this inequality and you can convince yourself that it does not matter that I'm going in E1 direction. I could go in any rational direction and the same thing will hold. And that's precisely what is used to prove this so-called shape theorem. So the shape theorem tells you that actually there is some shape such that the cluster at time t looks like t times a deterministic shape plus smaller order terms. And what this result tells you that in each direction there is a velocity, and in every rational direction is a velocity, and you can stitch together by some basic continuity argument to show that there is a shape. And of course, notice that here I only work with expectations. But if you are familiar with something called Kingman's ablative ergodic theorem, which is a random version of Pecquet's lemma, that will actually let you upgrade this convergence in expectation to convergence almost surely. So you actually have an almost sure velocity in every direction or every rational direction, and I can stitch together across all these directions along the sphere these velocities to make a shape. This is exactly what the shape theorem says by Cox and Retius. No. So this is, I'm just defining a new notation. So xmn is equal to t of m comma 0 to n comma 0. I just didn't want to keep these two coordinates in the subscript, so I just made this new notation. Okay.
How many samples do I need to estimate u versus accuracy?
Yes. So that question is very important, and that actually depends on what is the fluctuation around the limit shape. So because that there is a shape, so this is just like testing t-test, right? You need like epsilon square many samples because the fluctuation is like 1 over square root n. So if you knew the fluctuations around the limit shape, you would be able to tell how many samples do I need to, how much large time do I need to look at to estimate this accurately. But unfortunately, that's one of the very hard questions that we don't understand. Sure, obvious. You can do ZD, but here, Z2. Yes. So you need some sort of a translation invariance, because I'm using this fact that m to m plus n is same as 0 to n. So you need some sort of an ergodic action underlying this picture. So that is the where this Z structure is being used. But this kind of things you can do, in some other maybe Heisenberg group or something like that. But if you wanted to do, say, Cayley graph of hyperbolic groups, it would not work because different directions behave differently, right? You won't have, if you have a geodesic ray going from in a free group, say, in a free group of rank 2, if you are starting from identity and going to some direction in the boundary, all the edges along that geodesic don't look the same. Some are A edges, some are B edges, some are A inverse edges, some are B inverse edges. Whereas here, if you are going in the E1 direction, all these edges, they are the same. From the perspective of the model, there is no difference between those. So there is this underlying translation invariance that you have in this model, which is being used here, not specifically the Euclidean structure. Yes.
Z2 and I, right?
Yes, because the structure itself has a transition invariant, innate translation invariance, because when you translate in direction E1, you still get Z2. I mean, nothing is changing, and the IID environment remains IID under that translation. So if you are familiar with ergodicity, if the environment was ergodic rather than IID, something like this would still work. Okay, so you have a shape, and what do you know about a shape? Unfortunately, not much. So what you know is, by coming from triangle inequality, that this shape is convex. Some mild argument will tell you that it's also compact under some very general assumption, and it inherits all the symmetries of Z2 or ZD. Sorry. So B tilde T is not exactly the ball, because you are starting with a discrete graph, so you have to fill it in. So B tilde T is BT is the ball, and then you fill it in. Each vertex you replace it by a hypercube of size 1, because you have to take, I mean, you can't take a limit of sets in ZD and expect something continuous in RD. So you kind of have to fill it in. So that's why it's called the fat-end metric ball. Okay, so this is what you know about the first order behavior. So it's kind of all very nice and elementary. But then, of course, is the question that Sandeep asked. The next question you want to, oh, why is it not working? That. Oh, okay, fine. Okay. Yeah. So I will tell you before telling you more about this model, what is known about this model, which is basically nothing. Beyond the first order behavior, the model is very poorly understood. So anything what Sandeep was asking about, the fluctuations, that is not known at all. There are conjectures, which maybe I'll tell you later, but not much is known rigorously beyond this point. So let me tell you about some related models in certain specific cases which have been much better understood. And conjecturally, this model that I described also should behave in a similar way, although we do not know how to prove it. So this is a model which is called last passage percolation instead of first passage percolation. So what do you do here? So here you work in an oriented setup. So you look at the first quadrant of Z2, and instead of looking at all paths, you're only looking at paths going north or east, up or right path. And instead of minimizing over the weight of the path, you maximize over the weight of the path. Okay, so first passage means you minimize over all the weights of the path. Last passage means you maximize. So again, you see that the first order behavior, Fekette's lemma, that kind of argument still goes through, because here you do not have triangle inequality, but you have the reverse triangle inequality. The inequality gets reversed, but Fekette's lemma holds even for super additive sequences. So you get a similar first order behavior. But what is different for this model is that for certain choices of these distributions, I can explicitly describe to you what is the limit shape. So in the previous case, for the first passage percolation, what Sandeep asked, that is there a formula for the limiting shape? There isn't in general. For last passage percolation also, there is no general formula, but I can actually tell you that some examples. So in particular, if these distributions were exponential, I can actually give you an explicit formula for the limiting shape. And that makes analysis a lot more tractable. Actually, you know a lot more about the model, because this model is one of what are known as integrable models. So there is some Young-Baxter equation at the background that is being satisfied, which means that you can actually write down formula for distributions of several statistics in this model. Again, I mean, if you don't understand what that means, it's not important. But the important fact is that for a certain choice, so why do we care about last passage percolation model? One is that it's roughly similar to this first passage percolation model. Instead of minimum, you're doing maximum. So if you were allowed negative weights, then it would basically be the same. although there is a directedness, but not should not be very. And if you are a physicist, yes. So because we are only going up and right, given two endpoints, the length of gamma is constant because it's just the L1 distance between the starting and the ending points. Okay, so this is a model that is related, at least on the face of it. And if you are a physicist, you will say that, oh, they are the same model, they should belong to the same universality class. But the advantage is that this model can be analyzed. But before that, let me show you why, people did not come up with this model just by trying to say that, oh, I want to find a solvable model that looks like this first passage percolation model. This model actually arises in a very natural context of a different growth model, which is this Markovian corner growth model. So this is how it works. So at time 0, you have this interface. It's a V-shaped interface. It's usually referred to as wedge initial condition in physics literature. It means that the shape looks like a wedge. Now, how do you grow? So there is this corner, right? So you wait an exponential amount of time and you flip this corner. So now your interface becomes like this. Now you have two corners. Every corner, each of these two corners, you start an independent exponential clock. Whenever that rings, you flip that corner. Next one, maybe this one rings. So at this point, there are two corners again available. So this is a corner and this is a corner. Both of them will have their own exponential clocks running, and one of them will ring. No, it actually is going infinitely. So this is, this is, I'm drawing a finite picture, but actually this is an infinite. No, corner. A corner is a shape like a wedge. So this is. No, there's two. So corner, I mean only V-shaped corner. So V switches to lambda. So I'm always growing. So the corner, a V-shaped corner, switches to become a lambda-shaped corner. So I have two corners here. Any one of them can flip. This one becomes and so on. Sorry? No, it's so basically you should think about, let me just go. So you should think about this, rotate this picture 45 degrees counterclockwise. So after waiting x11 amount of time, so at time 0 you have this shape, at time x11 you have this shape. So you should think about these random numbers in these boxes as how much time you need to wait to flip that corner when that corner actually is available for you. Yes. And say the time to flip this particular vertex, it will be maximum of x11 plus x12 plus x22 and x11 plus x21 plus x22. So that's how this maps to this last passage percolation model, because you are maximizing over all possible paths. So this is a corner growth model, and you can also map it to like a sequence of zeros and ones. So every time you see a downward line, you call it a 1. Every time you see an upward line, you call it a 0. So at time 0, you have ones to the left of 0, zeros to the right of 0. And what does this do? This flipping mechanism that flips a 0 and a 1. So basically you can think about this. So that's how this model first came in biology, where they're trying to model some genetic network. So basically what you're doing is that you should think about these ones as particles, and particles are trying to jump to the right, but they can only jump if the next vertex is empty. So whenever you have a 1 next to a 0, there is a possibility of jumping for the 1 to jump to the right, which means that you are switching zeros and ones. So this is something that was introduced in 1960s in biology, actually, by MacDonald. And it turns out that this model actually is the same as this directed last passage percolation that I defined, where the waiting time, the edge, the vertex wait times are exponentially distributed. Exactly. So without exponential, you do not have a Markovian description of this process. Okay. So again, so this is, so you have also a different motivation for studying this kind of models. But what is our interest in studying that specific model of exponential last passage percolation if we are coming from, say, more a random metric point of view? It is this conjecture that that physicists have made and is empirically verified, is that under mild conditions on this waiting time distribution, it does not matter that you have exponential. You can replace that exponential by any other distribution, not too fat tails, let's say, and does not have too large of an atom at zero. The large scale behavior, which means the fluctuation around the limit shape, will be the same in that model as in the exponential model, and also in the general first passage percolation model. So this is the conjecture by physicists, which is empirically verified. You can run simulation and try to verify it, that the fluctuation behavior. So you all know central limit theorem, right? So when I have sums of random variables, IID random variables with finite second moment, then although the limit in the strong law of large number depends on the distribution, but the order of the fluctuation, square root n, and the limiting distribution Gaussian, that is independent of whatever distribution you start with. So it is a two-dimensional version of the same phenomenon that is conjectured here. So you have the same mechanism, although the distributions of these xij's might be different from case to case. That will change the formula for the limit shape, just as the limit in the strong law of large number depends on the distribution, is the mean of the distribution. Actually, you need something slightly bigger than second moment, because it's a two-dimensional thing. You actually need something like sixth moment. So, but it is conjectured that as long as you have high enough moments of this distribution, the fluctuation around the limit shape, that will be of the same order. So it's a universality. You should think of it just like you have Gaussian universality in one-dimensional growth processes. And what is the conjecture? The conjecture here is that the fluctuation would be strictly smaller than Gaussian, square root n fluctuation. So in one-dimensional random walk, you have the diffusive fluctuation. In distance n, you have fluctuations of the order of square root n. But here, the conjecture is that the fluctuation is some order n to the chi, where chi is strictly less than half, and this chi will depend on the dimension, but not on the direction in which you are going, nor on the exact distribution that you had. So this is what are called one of the universal scaling exponents of the model. So the universal scaling exponent for Gaussian universality class is one dimension is half. So this is some other exponent that is conjectured to exist, that will describe you the fluctuation for all these kind of models under very general conditions. Nothing particularly specific is needed. So they have, you can do a lot more, like, you can do, say, you can put weights. So you can consider positive temperature models. So instead of looking at the maximum, you can put a weight on the path depending on its length, and you can look at the free energy of the corresponding polymer model. So that is also expected to be in the same. Yes. So those things are all expected to be. So this is universal in a very general sense. So this is, so you have, why it is universal? Well, okay, so let me go there. So in physics terms, what you think is that there is, so the way it is growing, so a physicist way to explain this would be the following. So I have a Laplacian term which tells me that there is, so I have a growing interface, right? So h, x, comma, t, you should think of it as height of an interface at location x in time t. So there are two factors influencing the growth. One is the surface tension, which tries to make it more smooth. And then there is the nonlinearity, which tells you that the regions where the slope is high, you tend to grow more. So there is this competition between two effects and this additive white noise. So this is a stochastic partial differential equation, and very ill-posed stochastic partial differential equation, which Martin Harrer got a Fields Medal for making sense of this equation. But physicists, they are fearless. They define things when it doesn't make any sense. So Kardar-Parisi-Zhang, three physicists, came up in 1986 with this equation, and they say that all these general models, they satisfy these properties, that there is a surface tension which is coming from this curvature of this limit shape that you had. So there is some smoothing effect, but there is also this nonlinear term which is telling you that depending on the local slope, the rate at which you grow at that direction changes. So there is this nonlinear effect there, and the amount you grow, it is some random amount. So that's some space-time white noise. Yes. So this is kind of a huge body of work in the last 10 years, which shows that there are some models in this class as whose limit you get this equation, which is now called the KPZ equation. So what you can do with this equation is that there are these techniques that physicists have, which is called the renormalization analysis. So you kind of assume that the solution satisfies certain scaling, and then you try to understand under what scaling would the solution be invariant. I mean, you expect the solution to have certain kind of invariance built in, and you want to try scaling this h as some h epsilon, and you want to show for what power of epsilon you need to scale x and t by under, so that the scaled solution will also satisfy something similar equation, some similar equation. And doing this analysis, they predicted that in one dimension, you actually have this exponents 1/3. So remember that in one dimensional central limit theorem, the fluctuation at scale is n to the half. So here in 2 dimension, you expect that the fluctuation is of the order of n to the 1/3. So it's a much smaller fluctuation. And then there is this other exponent which I skipped because of Sandeep's question. So there is another thing which relates to the other question that I said. So there is this behavior of geodesics that I want to understand. And what do I want to understand? I want to understand how far the geodesic is from the Euclidean geodesic, which is just straight line joining the 2 points. And way to measure that is the maximum distance of the, say, this is the Euclidean geodesic, the L2 geodesic, and this is the random geodesic. And I want to understand how far the random geodesic can go from the deterministic geodesic. So this is something known as transversal fluctuations of a geodesic. And what you expect is that the transversal fluctuation is related. So if the transversal fluctuation is of the order of n to the xi, and the fluctuation of the passage time itself is n to the chi, then they're related by this simple linear equation called KPZ relation, which says that chi has to be 2 times xi minus 1. So if chi is 1/3, as I showed you in the next slide, then xi will be 2/3. So that tells you what? That tells you that if you go in distance n, then the fluctuation in the metric or the height, whatever you want to interpret, will be of the order of n to the 1/3. And if you look at the geodesic that attains this maximum or minimum weight, the geodesic will typically be at distance n to the 2/3 away from the straight line joining the endpoints. So these are things that are conjectured based on this non-rigorous analysis of the stochastic partial differential equation by introduced by these people. Okay. So, and actually you have much more finer predictions that are available for these models. So beyond the exponent. So exponent tells you what is the scaling, but in central limit theorem you also know that the limit is Gaussian. Right, so you can ask what would be the limit be here, and that is also predicted and known in some cases. So this is known as what is called the Tracy-Widom distribution. So it's a distribution that first arose in random matrix theory. So you get as a limit, the analog of Gaussian in this particular universality class, which is by the way called the KPZ universality class after these people. So the role of the Gaussian limiting distribution is played by a distribution called the Tracy-Widom distribution, which is also the limit of the distribution of the largest eigenvalue in several random matrix models. So if you know what is Gaussian unitary ensemble, which means that you have like an n by n matrix where on the on diagonal you have Gaussian with 0 mean and variance 1, and off diagonal you have complex Gaussians, and below diagonal you take the conjugate of that, so you get a Hermitian matrix. So the largest eigenvalue of those matrices appropriately scaled converge to a distribution which is not very explicit like Gaussian. It does not have an explicit density like Gaussian, but you can write down formulas for that. So this is called the GUE traceoidom distribution, and that distribution plays the role of this distribution of 1-point scaling limit that Gaussian plays in the one-dimensional story. Okay, so let me now come to the second question, and are these things actually explaining what is happening in real world? That's kind of an interesting question. Otherwise, why are you studying all this? I mean, they are interesting mathematics. What? Yes.
Hard problems.
Yes.
And they've been out there for a long time.
Yes.
Do you believe that there's a new technique needed that will work, or is there some kind of, class of hard problems is always a bit hard?
You mean, are these like NP complete problems that you know that you'll never be able to solve? No, I don't think. I mean, I think these problems, I mean, at least in 2 dimensions, they are, I believe that they could be solved. But in higher dimensions, it's hard because in higher dimensions, things are, I mean, even at the conjectural level, even physicists don't agree what the values should be. And even, it's not even clear whether there should be some nice value like half and 1/3 in higher dimensions. So in higher dimensions, I don't know if the problems are, but in 2 dimension, I believe that these problems can be solved.
This could be a task for for intelligence.
They haven't, I mean, ChatGPT is getting better and better at solving undergraduate mathematics problems, but they haven't quite reached the level of doing this type of problems. I think, maybe GPT-7. So we will see. They haven't taken our jobs yet. Yes, I mean, for solving undergraduate problem, any problem that they could not solve last year, they can solve it this year without any prompt. Yeah, so maybe GPT-7 will take all of our jobs. So we'll see. We'll wait and see what happens in a few years, but not yet. Yes. Or minimum. I mean, this is all conjectural. It applies to both up to a change of sign. So for the maximum, it should be the traceoidom distribution. For the minimum, it should be the negative of traceoidom distribution. Just that, because maximum and minimum is just up to a change of sign. So anyway, so this is so actually when should I stop? 10 minutes. Okay. Yes. Indeed, but if you think about it, you are trying to minimize, right? So you wouldn't do too much of a backtrack. So, but these are all asymptotic behaviors. These are all asymptotic behaviors, right? So if there is a microscopic fraction of backtrack, you wouldn't see that in the limit. So that's why you expect it to be the same, because unless you are putting a large weight on 0 in the weight distribution, you expect that there wouldn't be too much of a backtrack. So largely the paths would still be directed. All of this is conjectural, but heuristically it's believable. Okay, so anyway, so maybe since I don't have too much time, I'll just tell you a little bit about, are these things actually things that you see in physical world? The answer is yes and no. So there are many cases where you see this behavior, but it's not also completely universal. Not every picture that I showed you follows the predictions of this KPZ universality class. So this is one that does. This is a bacterial colony growing in a petri dish, but not the E. coli one that I showed. The E. coli picture that I showed, it does not follow the KPZ thing. This is, I forget what is the name of the bacteria, some agar something. This condition it does, in certain kind of condition it does not.
Yeah,
I mean, this is already very simple in terms of, at least, in terms of simulation and all. Analysis maybe is not so simple, but at least in terms of how you generate this model, these models are already very simple. So that you get explain this very complex behavior by a reasonably simple to describe model is already quite interesting. Okay, so this is like this edge of burning paper that also again this sort of depends on how fast the paper burns. In a slow combustion regime, actually it seems to satisfy this KPZ type growth. So this is some experiment from liquid crystal, yes. Yeah. So you take a piece of paper, you put a flame here at the bottom edge, and then it kind of burns, right? I mean, you have, and how do you put a flame? No, I mean, you can even start it at a corner. It doesn't really matter, right? I mean, you can start. I don't know if you have never done this thing before. This is something. It's a pretty common. So this is. I mean, you can start it at a corner. I mean, depending on the initial condition, the exact shape might be different, but the fluctuations would be the same. So you started at a corner, and then sort of near the corner, these edges are burning, and I mean you can do this yourself if you so feel like, and you'll see that there is some jagged shape around some reasonably nice looking curve. So this is something some experiment from liquid crystals. They have something called dynamic scattering modes. I don't know what exactly that is. Don't ask me. But this is an interface between two types of dynamic scattering modes. They call it DSM1 and DSM2. This actually like matches very well with the KPZ prediction. And this is a quite interesting paper from Nature from about 10 years ago. It's like, if you spill a drop of coffee in a paper and let the stain dry, you'll see that, coffee drops somewhere and then the stain sort of expands, right? And whether the, and you can look at this expanding stain as a random growth model, and you want to ask this edge of this stain, how does it look like? And it turns out, at least that's what these people showed in this Nature paper, that if your colloidal particles in the coffee is ellipsoidal rather than spherical, then you actually do get excellent experimental agreement with the KPZ fluctuation. So this is the spherical beads. So the colloidal particles are spherical. Here you do not see the KPZ fluctuation. Here you have ellipsoidal beads. You see KPZ fluctuation. No, there is some colloidal particle in the drop of the coffee. Right? Those particles could be either spherical or ellipsoidal. So again, I'm neither a coffee expert nor an expert in this this part of physics. So you can look at this. This is a quite famous paper from Nature in like 10-15 years ago. So you can look at the exact description of this. So there are actually. So it turns out that you actually have pretty interesting models which experimentally at least agree very well with these kind of prediction. But okay, so again, now I've spent enough time to in selling the area, but let me try and put back on my mathematician hat and tell you a little bit about what are the things that are known, and you will see that why this problem I have described it to be difficult, because the things that are known rigorously are quite far from the truth. So say the fluctuation bounds, right? So that's the second thing. First order we know by the shape theorem. Second order is the fluctuation, variance of the passage time. So we want to understand. So remember, in 2 dimensions, the predicted order of the variance is n to the 2/3. What do we know is that we know that the best upper bound is n by log n, and best lower bound is log n. So we don't even know that there is a lower bound that is polynomial. So the correct behavior should be n to the 2/3. We are very far away from there. So what people have been trying to solve this problem at least for the last 40 years or so, and it has turned out to be quite difficult. So as mathematicians do, they try to make further assumptions under which you can maybe show something. So there is one assumption that has been made, which is this very severe restriction, that you restrict to this very few class of models which are exactly solvable, like this last passage percolation with exponential weight. So there what happened, there you basically know everything now. like last 20, 25 years of intense work, you know everything. In particular, you know the order of the fluctuation, you know the distribution limit. This is the Gaussian trace-Ulam, GUE trace-Ulam distribution, and lots of other things like transversal fluctuation exponent of 2/3, you know, like process convergence to Airy process. Again, I mean, if it doesn't mean anything to you, it doesn't matter. But instead of just looking at passage times between 2 points, you can look at passage time between all pairs of points, and you have some joint convergence result. So this you should think of as an analog of Donskir's invariance principle. I don't know if you're familiar with this, like random walk converging to Brownian motion. So the analog of that also is known in this setup if you are working with this exactly solvable model. But the drawback is that you are really looking at very, like there are 4 or 5 models which are solvable like this. And these analysis depends very crucially on this integrable structure, which, I mean, somewhere there is a Young-Baxter equation hidden there. So this you really cannot extend to more general models. So that is one line of one line of work that people have done a lot. But there are also other kind of models that people have tried to investigate. Is that what if you impose some extra symmetry of your model? In many cases, if you have extra symmetries, that makes models analyzable. So one particular thing is that you can impose some models with rotational symmetry. So this is something people do actually these models are introduced by some computer scientists anyway, because first passage percolation in some sense, it's something like some optimization problem in a network, right? I mean, you're trying to minimize the cost of cost of a road network or something like that. So there, instead of having the vertices exactly on a lattice, you choose this vertices along like some Poisson process, and you look at the Delaunay triangulation. I mean, look at the Voronoi cells of this this point process. So basically, the cell of each vertex is the set of points such that this vertex is the closest among all the Poisson points in the. So every vertex, this cell, this vertex, the cell consists of points in the plane whose closest Poisson points is the center of the cell. So this is called this is called a Voronoi diagram of this Poisson point process. And you can ask how many Voronoi cells I have to cross to go from one point to the other. That would make a first passage percolation model. This is called a Voronoi first passage percolation. Now the advantage is that because you have start with Poisson point process rather than the lattice, now you have a lot more symmetry. In particular, you have rotational symmetry. So if you have rotational symmetry, then yes, 2D Poisson point process. So these points, these black points, are Poisson points of a process, and then you make these Voronoi cells out of that. So you're asking how do you simulate that model? Yeah. No. So this is like I have, if you are not worried about simulation, maybe I should wrap up in 1 minute or so. So if you have, you can define the model on all of R2. You have a Poisson process on all of R2. I mean, if you want to ask how to store that in a computer, that's a different question. But theoretically, you can define a Poisson process on all of R2. And then you can talk about Voronoi cells of each of these points. That will give you a partition of R2. And then you can ask, like, between 2 Poisson points, how many Voronoi cells I need to cross to get from one point to the other. If I'm just only allowed to cross, if the only edges are allowed like this, between 2 neighboring cells. So that would make a first passage percolation model, which, because of the underlying Poisson process having additional symmetry, will become rotationally symmetric, rotationally invariant. So for these kinds of models, now we have some results which were not known before for the lattice models. You can get some concentration bounds, you can get some improvement of the variance, some this scaling relation that I described to you, that can be obtained rigorously. Actually, the improvement of the variance does not come for this Voronoi model, but some other rotationally invariant model. But the point is that if you impose some extra symmetry, you can get much stronger results, but we still can't get the actual 1/3, 2/3 yet. So we get more than what was known before, but still not there yet with the exact values of the exponent. But anyway, so there are many interesting questions that that still remain. I think I'll just stop here. Thanks for your attention.
Not with, let us try to speaker again. On behalf of Ashoka and ICTS, we'd like to present